Hello 20-2 students. So today we're looking at lesson 1.4, which is deductive reasoning. So we're going to start out by looking at something called a proof in this lesson. And if you remember in our last lesson, we looked at something called a counterexample, which is basically where you have an example that proves that a conjecture is not accurate. And a proof is basically a mathematical argument that shows that a statement is valid in all cases. So it's basically telling us that no counterexample exists. Because if you remember in the last lesson, we talked a little bit about how it could be tricky to figure out for sure if a counterexample exists because, you'd have to keep going through more and more possibilities, right? So, and that can be pretty time consuming. So this idea of the proof helps to kind of reduce that sense of like, I need to find a counterexample and I might have to go through a lot of different lines of inductive reasoning where I'm actual numbers to test whether or not, there is a counterexample. So with deductive reasoning and proofs, what we're doing is we're making a generalized statement that's not just a specific example, but it can be applied to all possible examples to prove whether or not the statement is valid. So we'll look at an example of how that works down here. So keep in mind a conjecture is only proven when it's been shown to be true for every possible case. So if you remember again in last lesson, we said if you have even one example, like one counterexample, then the conjecture is false, right? So we have to know that every possible case our conjecture will be proven and that there's no counterexample if we want to say that that's true. So we accomplish this by creating this generalized statement or equation that I just mentioned. Now keep in mind an example is not a proof, okay? So where we looked at last time where we would make multiple examples until we found a counterexample, what we were doing in those questions was to take actual numbers and just keep trying them over and over again, right? So what we're about to do now is a proof, not an example, because instead of just using numbers and continuing on with the pattern until we find a counterexample, we're going to make a generalized statement that would apply to all possibilities of like the conjecture. So for this one, in this example, we have a math student noticing an interesting number pattern when adding integers. So 1 plus 2 plus 3 plus 4 plus 5 is equal to 15. Negative 15, 14, 13, 12, 11 adds up to negative 65. Negative 3, negative 2, negative 1, 0, 1. If you add those together, you get negative 5. Maybe pause the video. Oh, actually, no, never mind. I already mentioned it down here. If you want, you can pause the video and see if you can figure out what the pattern is. But I do actually tell you down here. So they make the conjecture that whenever you add 5 consecutive integers, the sum is always 5 times the middle number. So if we look here, we have 5 consecutive numbers being added. The middle number is 3, and the sum is 15, which is 3 times by 5. Right? For this one, the middle term would be negative 13. Negative 13 times by 5 is negative 65, which is what we get there. And then for this one, our middle term is negative 1. Negative 1 times by 5 gives us negative 5, which is what the sum is. So they want us to write a proof that shows whether this conjecture is true for all integers. So basically what we want to do here is use variables to see if this would be accurate. So the statement is that if you add 5 consecutive integers, the sum is always 5 times the middle number. So basically if we start out with our first value is x, let's say, and then we add on a consecutive number, which means a number that's 1 higher than x, so it's going to be x plus 1. Okay, and then we have to add 5 of those. So the next one is going to be x plus 2, right? Because it would be like, in this case, if 1 was x, x plus 1, or 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5. So now we're going to have plus x plus 3, and then plus x plus 4. So now we have 5 consecutive integers, 1, 2, 3, 4, 5. And the statement is that the sum, so we put in our equal sign to show that we've added all these together, the sum is always 5 times the middle number. So in this one, our middle number is x plus 2, right? Because there's 2 values on either side of it. And they're saying that the sum is going to be 5 times that value. So basically, it's going to be 5 times x plus 2. Okay, so that's fine that we wrote that out, but of course what we want to do is we want to get our proof down to the point where we can see whether or not this whole statement actually is equal to 5x plus 2. So in order to do that, we need to start to simplify these terms, okay? So whenever you're adding things together, like for example, nothing in here is being multiplied, right? So it's basic. I just put these in brackets so we could keep in mind what our what each term was, but technically we're just adding them together. So in that case, you just want to add like terms. So we have 1x, 2x, 3x, 4x, 5x. So we basically have 5 x's. So x plus x plus x plus x plus x. And then if we add together our other like terms, which are numbers, we have 1 plus 2 plus 3 plus 4. Okay, and we're going to leave this side as it is for now, plus x plus 2. So what happens when you add 5 x's? Remember that when you add variables together, however, if they're all exactly the same, you're basically just adding them and putting the coefficient out front. So in this case, we have 5 x's. So we're going to have 5x plus 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. So 5x plus 10 is 5x plus 2. So now at this point we would want to see, is there any way we can make these two equal to each other? That's, it still has to be obviously mathematically sound. So in this one we just have a single x, right? So how would we make 5x into just x? We would have to divide this whole thing by 5. Right? Because then our 5's would cancel out, and 10 divided by 5 gives us 2. So if we divide the 5 out, we put it outside the brackets. 5 divided by 5 is 1, so we're left with just x, and 10 divided by 5 is 2, so we have plus 2. And on the other side, we still have 5 bracket x plus 2. And so at this point, we can say this is accurate, right? 5x plus 2 is in fact equal to 5x plus 2 because they're the exact same thing. So this proves that the conjecture that was made here is correct. So with the proof, you can see that we're not just going through example after example trying to prove it or find a counterexample. We are making a generalized statement by using variables to prove that this is correct for all cases, right? Not just for the individual examples that we try, okay? So when we're doing this, we're doing a form of deductive reasoning, and this is where we draw a specific conclusion, so in this case, the conclusion that that conjecture was correct, through logical reasoning by starting with general assumptions. So this is really important that we're using general assumptions in this type of question. That are known to be valid. So deductive reasoning is used to create a proof for a conjecture, which is what we just did. Now, it's not always going to apply to like number type questions like we just looked at. We can also apply it to reasoning. So in this example, we just have a verbal statement. Weightlifting builds muscle. Muscle makes you strong. Strength improves balance. Okay, so we kind of have this sequential idea that weightlifting is something that builds muscle, which makes you strong. And when you are strong, you have improved balance. So it says, Inez lifts weights. What can be deduced about Inez? So basically with this, using deductive reasoning, we want to kind of make logical conclusions between these statements. So if Inez lifts weights, that means she has built muscle, which makes her strong. And because she would be strong from that, she should have likely have good balance. Okay, I'm not going to waste the time writing it out, but you guys will see in the filled in notes the properly written out version of that. So basically, Inez lifts weight, which would build muscle, which makes her strong, and therefore she would likely have good balance. Okay, so you're logically connecting all of these statements to make a deduction about a specific statement. So again, see how that with deductive reasoning we have generalized statements that are being used to prove a specific statement, which is about Inez. Okay, now one kind of tool that we can use when we're doing deductive reasoning is called the transitive property. And this is that if two quantities are equal to the same quantity, they're equal to each other. So for example, if we say A is equal to B and B is equal to C, if A is equal to B then and B is equal to C, that means they all have to be the same. So therefore we can say A is equal to C, right? Because they both equal the same thing. Another example would be if Troy is in the same row as Bella and Emma is in the same row as Bella. So Troy in same row as Bella and Emma is in same row as Bella. Okay, I'm just going to do that. So Emma's in the same row as Bella, Troy is in the same row as Bella. What's a conclusion that we can then make? Well, if they're both in the same row as Bella, Troy and Emma must also be in the same row. Troy and Emma in same row. So you can see how we can apply this again. This is kind of the deductive reasoning with the transitive property. We can apply this to a logical statement, kind of like we did with the previous example, or we can apply it to more like a mathematical type concept where we're equating values. Now, when we're doing deductive reasoning, a lot of times one of the tools that we'll use is something called a two-column proof. So basically all it means is that you're making your statements in one column and the other one you're providing the justification in that column. Okay, so I'll show you an example of what I mean by that. Use a two-column proof to prove that angle AED, maybe I'll just grab my highlighter, AED and CEB are equal. Oh, look at that. That pretty much just highlighted the whole thing. I don't know if that helped. Maybe what I'll do is this. Highlight that one in one color and highlight this one in the other color so we know what we're trying to look for. There we go. Okay, so those are the two angles we're looking at. So basically with a two-column proof, you put your argument or statement on one side and then your justification on the other. Now for this one, we're going to assume we don't have any knowledge of trig statements because these are opposite angles, but we're not going to use that. We're going to use deductive reasoning, okay? Because the rule of opposite angles was developed through deductive reasoning. So what could we come up with as an argument if we want to say this angle is equal to this angle? The first thing that we could show is, let's see, if we have a whole straight line here. So what you want to start out with is which angles do you actually know, which we don't actually know the measurements of any of these, except we do know for sure that a straight line makes 180 degrees, right? So we know that if you were to add angle AED with angle AEC, you would have 180 degrees. So let's put that down. AEC plus AED equals 180 degrees. Now, because we're trying to prove the same thing over here, is there a similar kind of a statement? Well, obviously this line that we just looked at where there's angles going on top of it, there's the same thing happening on the bottom. So angle CEB plus angle BED, angle CEB plus angle, oops, I forgot to put the angle here, BED equal 180 degrees. And for our justification for these, we can just put that it's a straight line for both of those. Straight line. Okay, so let's see if we can rearrange these so we can get a statement for the angles we're actually interested in, which is AED and BEC or CEB, whatever. Actually, that's kind of, usually when you're writing angles, you always write them kind of in alphabetical order, so maybe I'll just try and keep that one a little more accurate, so it should be BEC. Oh, and I didn't do that there. Oops. Okay, so let's rearrange this so that we have just a statement for our ones that we're interested in. So AED is equal to, angle AED is equal to, if we move this AEC away, it's going to be 180, and because these two are added, we have to subtract it. So 180 minus angle AEC. Oh, and I forgot to put in the angle again. Angle AEC. Okay. BEC minus BED. Actually, you guys, I think what we might want to do here instead is, because we want to prove that AED is equal to CEB, so now that I see the proof for AED, we want to try and, it's 180 minus AEC, so AEC, if we were to use this straight line instead of this straight line for this one, then we could show that angle CEB is going to be equal to the 180 minus AEC, which is the same as what AED is, and then by the transitive property they would be the same. So what I'm actually going to do is go back to this first one and show angle BEC plus angle AEC, they're still equal to a straight line. So angle AEC, I'm going to change BED to AEC. See, and with a lot of times with these types of questions, don't be afraid if the first time you don't get it. Like, you can always go back and change things as long as you know to look for these kind of patterns, right? Where we know that we want to try and find something that where we can say that these two things are equal. So in order to do that, we needed to use the same reference angle, which in this case was AEC. So now I can say angle BEC is equal to the same thing, right? If these two added together were 180, BEC, we would have to subtract AEC from both sides. So it's going to be 180 degrees minus angle AEC. So now we can say, and these ones are kind of weird because it's like justification. So we could either say algebraic rearrangement, I don't even know. And that's another thing for you guys to be aware of. I think a lot of students are really concerned when they go into this, like, how do you come up with the name of the justification? Honestly, you guys, if you know what you did, like, anything that you say that's reasonable, because the other one, I think on the filled in notes I had rearrangement. I think I just had subtraction written in there, which is okay as well. So basically, as long as you're just making a statement that makes it clear to me that you understand that this was a logical step to make, right? So for this, if we both just rearrange the statement algebraically, we haven't changed anything in it. We've just moved around the terms. So now we know that we haven't like done anything to change this to suit our needs. We've just rearranged it. So now that we've rearranged that, because both AED and BEC are equal to 180 minus AEC, we can use the transitive property to say that they have to be equal to each other. So basically we would say AED, or sorry, just to make that easier to write out so I don't have to write out two lines, I'm just going to say 180 minus angle AEC is equal to both AED and BEC, right? So, and I don't know if, I mean, I guess we could say that's transitive property. So transitive property, which if we apply it to that, then we can say AED equals BEC. Okay, so the thing I want you guys to take away from this is when you're doing this two-column proof, don't get super stressed out about like whether or not you're using the exact right words or names. Like as long as you're giving me a reasonable explanation for what you did here, that's okay. Okay, so, and some of the more formal names you should know, like the transitive property that we use there. That'd be the main one that we've looked at so far. Okay, so that's everything for this lesson. Next time we'll be looking at proofs that are not valid. So I will see you in that lesson.